So we've been through the integration to find electric field due to continuous distribution of charges, specifically for lines of charge like a thin wire, a thin rod. We talked about the ring. Our author, so this is for the physics, for scientists and engineers, book by Randall Knight. I'm going to go through the other equations that are derived and that we have in our test notes so that we won't need to derive them. But we do need to know when they are applicable and when can we use them. So I'm just going to start, and I'm going to go ahead and reiterate E for the point charge, because that's the first one listed in our section with electric field equations. So 1 over 4 pi epsilon naught Q over R squared R hat. Again, the 1 over 4 pi epsilon naught is the constant we've been using. So I wrote the equation as KQ over R squared before. Q being the amount of charge on that point charge, R in the denominator being the distance from the point charge out to where we're trying to find the electric field. And then R hat dealing with that radial direction. The electric field either points radially away if the charge is positive, or it points radially towards if the charge is negative. Next to that equation, we have E of a dipole on axis I just wrote E there. So 1 over 4 pi epsilon naught 2p over R cubed. It's an R. And then E for a dipole. That's perpendicular to the axis. This equation, 1 over 4 pi epsilon naught P over R cubed. Now, I did talk about the electric dipole back in the electric field video. An electric dipole is specifically two equal but opposite charges. So both of them are Q. One's just positive, one is negative. The dipole moment, P, which is listed next to these equations, is equal to Q times S. Q being the magnitude of the charge, either one, S being the distance between them. So this line here is what we mean by the dipole axis. So the dipole moment, Q times S, the distance between them, these electric field equations up here both have P, meaning this Q times S. The vector P, the dipole moment vector, points from negative towards positive. So this first equation, the dipole on the axis, means somewhere along the axis, either way, left or right. But this equation is specific to R being much, much bigger than S, to the point that these charges essentially look like they're overlapping. So S is an insignificant number compared to how far away. So R, we essentially see these two charges on top of each other. R would be measured from where they're at out to the point we're trying to find the field. So this would be our dipole right here, as if I zoomed out. So on axis just means along this line of the dipole axis, the line that connects the two charges. The other one, perpendicular to the axis, going out this way, perpendicular to the line that connects them. In both cases, we're assuming we've zoomed out far enough that the charges are essentially touching. They're not really touching. We've just zoomed out, for example, like this, far enough, which I'm not going to go too far because I want to be able to get it back. But far enough that those charges appear to be on top of each other, to appear to be at the same point. If we were dealing with a situation where they're not far away, we would simply be finding the electric field due to multiple charges. They're both point charges, so I would find the electric field due to one of them, wherever it is we're trying to find the field at, plus the electric field due to the second one, and add them together vectorially. So point charges, I would grab the equation, find out the value of the electric field for them individually, and add them up. And this works well for a few charges. We did some examples that had 3 charges. But we do eventually get to the point where there are too many to really add up that way. And that's where the integration comes into play. We are still adding up, but we're adding up a huge number of point charges. So this is our integration, where we did, for the example, a thin wire or a thin rod. Some sort of linear charge density. Technically, integration can be done for surface charge densities and volumetric charge densities. We're not going to ask you to integrate in those situations, but you do need to know how to set up the integration in the case of a thin wire or thin rod. And by this, we essentially mean a finite length. So if you remember the quiz question where we had charge all along the, not all along, but for a portion of the x-axis, and then we wanted the electric field at a point here, we knew we would end up with some sort of positive x and positive y component of the electric field. This is a situation where we would need to set up the integral and solve for the x and y component if we wanted both. The other example was where we wanted to find the electric field on a line that's on the axis of that wire or rod. So those are 2 points or 2 situations where you will need to integrate. Now, the author has done a couple of these situations for us, not this specifically, but when you see E of the rod, this is a very specific situation. It's not for every rod. I'm just writing the equation first. So it would be a finite rod of some sort, like I just mentioned. But this is solved assuming the point of interest is exactly in the middle. So half of the rod's this way, half of the rod is this way. And that's why to the right of the equation it says above the midpoint of a finite rod. So if you know the point you are interested in is exactly in the middle, then you can use this equation. But if you see something like this over here on the right where the point is not exactly in the middle, then no, you will need to integrate because this solution over here won't work. Now Q is the total charge on the rod. R is this distance just straight from the rod to the point. L would be the length of the entire rod, which is why I wrote L over 2 on both sides here. So this equation will work great if you know you're using it in the right context. The equation next to it, E of a line. I will explain this one as well, of course. So as it says to the right of the equation on the test notes, it says infinite rod. What that means is if I just add on to the picture above it, the charge distribution goes on forever in both directions. It doesn't end. And so in that case, there would be the x components that always canceled out, and we would end up with only a y component of the electric field. So in this specific equation, lambda is the linear charge density. R is the distance, just perpendicularly from the line or rod out to the point of interest. This equation is solved by integration, where your limits are from negative infinity to positive infinity. And this is what the solution simplifies to. Okay. So as far as a thin line or rod or wire, you're either going to integrate or one of these is going to work. But be careful to make sure when these all work so that you are choosing the correct equation for the problem you are solving. The next line in the test notes that we have is for the ring and also for a disc. So in the previous video, we derived this equation for the ring. It says specifically on the z-axis. Recall that the z-axis always represents the axis that goes through the absolute center of the ring. Z is always measured. It's the distance from the center to whatever point on the ring that you're trying to find the field at. Q is the total charge on the ring, and capital R is the radius of the ring itself. So the shape, the wire has to be bent into a nice circle. Next to this, we have E for a disc. I believe they do this integration in the book where they add up all of these rings until they make up a full disc. But they've given us the solution and we will go ahead and use it. So just writing out the equation. So the general setup is the same. It's just that we have a solid disc and not a ring. The z-axis is still going through the center of this disc. Z still is the distance from the absolute center out to whatever point we're trying to find the field at. Capital R is still the radius of the disk as a whole. Now, eta here is the surface charge density. Meaning the charge per area, because the charge is spread over the entire disk. Epsilon naught is our constant, not the 8.99, but it's the 8.85 times 10 to the negative 12. It's within the chapter. It's in the test notes. You don't have to memorize this, but it is a constant. Okay, so a ring, a disk. The next line has a couple more equations for us. E of a plane. What we mean by that is something that's very, very large. So this could be an infinitely large disk or rectangle, but something that is very, very big compared to any distance z away from it. In fact, if we look at the equation for the disk and we make and plug in saying that r is much, much greater than z, the second term in the disk equation is going to go to 0 because that denominator is going to be very, very large in comparison to z. And that's how we end up with this eta over 2 epsilon naught. Essentially, the electric field is constant anywhere near a very large flat surface. That's what we mean by a plane. A flat surface of some sort. Doesn't actually matter if it's a circle or a rectangle or a square, triangle. It just needs, its dimensions just need to be really large in comparison to where you're looking for the electric field. E outside of a sphere. Notice this is the same equation as for a point charge. We'll actually show in the next chapter why this is the case. There's an easier way to show it than by integration. So the Van de Graaff dome, for example, where we can have our hair stand up. All this excess charge, if it's a conductor, that excess charge would be on the outside. It turns out we can calculate for the electric field outside. So this distance, lowercase r, from center to where we want the field, must be bigger than capital R, meaning the radius of the actual charged sphere, the charged object. This does work on the boundary as well, if lowercase r equals capital R. But the point charge equation works. But the distance has to be measured from the center of the sphere, not from where the charge is, but from the center. Okay, one last equation for electric field specifically. Yes, there are a lot of them. That's why I'm going through them so that we hopefully will know how to work with them. E of a capacitor. By definition, a capacitor is two planes. So remember over here on the left, it's mostly out of sight, E of a plane. It is two planes that are parallel to each other with equal and opposite surface charge densities. So both planes have the same magnitude of surface charge density. One plane is positively charged, the other plane is negatively charged. Well, the plane on the left is positive, so it's going to create an electric field to the right on its right side, to the left on its left side. I'll draw it over here too. This left plane is negative. That doesn't represent an electric field. I was just pointing to the plane. So electric field lines point towards negative, towards negative, towards negative. So essentially, the electric field on the outside ends up canceling. So what we mean by E of the capacitor is inside, the electric fields are in the same direction. So if I called this plate 1 and plate 2, and I wanted to find the total electric field in there, I would need to add those together. But again, our capacitor, we're saying both planes have the same eta. I'm putting absolute values around it, again, because we've already accounted for the directions. So in my picture, these will both be in the I hat direction. So we end up with 2 eta over 2 epsilon naught in the x direction. The 2's cancel. That's where this E of a capacitor is eta over epsilon naught comes from. Simply from adding E due to the 2 separate planes. The I hat here is specific to my picture. It points in the x direction. But again, both planes must have the same surface charge density. This equation is just substituting in that ratio of charge per area for surface charge density. So you can write the equation both ways. So quite a few equations for electric fields. You will want to be familiar with when each one of them can be used, what situation they're applicable for. I'll do a few examples next that will hopefully help as well.